Hey guys, in this video I'll show you how to create a volumetric fog that is not actually volumetric, but looks like so. It's one of those things where, as a tech artist, you could find yourself banging your head on for several days straight, trying to fake something our modern machines aren't yet capable of render in real time. I'll try my best to walk you through a series of different approaches with increasing difficulty levels. Each one of them takes the previous one a step further, so make sure to enjoy the journey and think about how and if you would have done things differently. So, as always, let's start from the basics. As I showed you in my previous video about post-processed materials, to display the scene, you need to sample it. Now, to create the simplest fog possible, we can execute a simple interpolation of the scene color to the fog color, based on the distance of the surface from the camera. In fact, all of us know from life experience that what the fog essentially does is to uniform the color of what we see the further we look. So, to recreate such effect, we could think of using the depth pass data after some rescaling as alpha for the interpolation I was talking about. Let's grab the scene depth and divide it by the length of the fog fade-in we want to have. And use this to interpolate the scene color as discussed earlier. Strangely, our shader seems to darken the scene instead of creating a nice mist. Why is that? Since the material is set to run before the tone mapper, the high dynamic range of the illuminated scene has not been converted to low dynamic range yet. And since this scene has a physically accurate lighting, the pixel colors after the light pass are way beyond the usual 0-1 range. We could switch it to be applied after tone mapping and the fog would work fine. But at the same time, we would lose the contribution from other post-processes, like the temporal anti-aliasing, and the jittering would create a very disturbing flickering. So, instead, the best thing to do is to give the fog the proper intensity, accordingly to the scene lighting. Now, it's time to point out a detail that is quite hard to notice, but does its part for the final quality of the effect. Let me contrast the fog gradient to make it very apparent. And move to a more open area for clarity. As you can see, our fog is drawing a straight line on the ground. And if I look around, it's even more clear, since on the viewport sides we see the fog turning with us. Wait, shouldn't the pixel depth output the distance of the pixel from the camera? The answer is yes, but the distance is given in the camera frustum space, so it is a bit different from how we intend it. In fact, if the fog is at a certain uniform distance from my eye, like in this case, I would expect it to draw a circle all around me, not a straight line. To fix that, we have to calculate the actual distance of the pixel from the camera by ourselves, which is easily done by quite literally translating the last sentence to nodes. And now everything makes much more sense. Moreover, we can give the fog gradient a quadratic contrast curve to make it much more natural. Even though our fog creates a lot of mood already, it is still a boring uniform layer over the scene. To make it more realistic and give it some consistency, we could break it up a little bit and animate it. We can quickly do that by mapping a cloudy noise on the screen, make it slowly pan and use it as a mask for the fog gradient. The mask adds the right type of character to our fog, I'd say. But the variation looks a bit too strong to me. We have points where there's no fog at all. Let's try to make it smoother by controlling its contrast curve. In that regard, one thing that you often see me doing is squaring the gradients. This operation has the effect of making the smallest values even smaller, while having less and less effect the more we approach values near 1. This visually translates to a complexively darker gradient, but in this case we want the opposite. So before and after the squaring we are going to mirror the values, making the flipped contrast curve darker, which will result in a lighter one once we mirror it again. Better, but still too many holes in our fog. While we're there, let's also make the minimum values a bit higher. We already obtained a fairly good looking fog for a still camera. In fact, even a not so observant eye would immediately notice that our fog looks like an animated image slapped in front of the camera while looking around. To address this issue, we must rethink the way we are computing the mask UVs for sure. A solution could be to compute some spherical UVs around the camera. Let's try it and see what happens. To do that, we can start from the camera vector data. This node outputs for each pixel a normalized vector that points from the surface in the scene to the camera. To create the first component of the new UVs, we have to convert the first two components of the camera vector from Cartesian to polar. Well, we actually need just the angle. We don't care about the length component in this case. To have that, we just need to calculate the arctangent 2 of these two components. Now, for the second UV component, we have to use another inverse trigonometric function, the arcsine. Both these nodes output angles in radians. To normalize their ranges, we have to divide them by pi. Before applying these new UVs to the texture, let's visualize them to better understand what we just did. As you can see, we basically created the UVs of a sphere inside, which don't rotate with the camera. Now we can finally plug everything in and looking around is not a problem anymore. We can improve on this by adding multiple layers to our fog mask. In fact, it doesn't make much sense that we see the same noise scale everywhere in the scene, independently of how far we are looking. The further we look, the smaller the noise should be, right? So, let's sample the texture 2 more times and, for each copy, let's increase the tiling. Let's also make each copy pan slower, depending on how tiled it is, and in a slightly different direction for variety. We can't simply combine these 3 masks now though. Since each new copy should start to affect the scene at a further distance, we have to create a distance gradient for them. We can base our new gradients on the main one, so we can work in the 0-1 range and everything will be responsive to the fog fade length parameter. Okay, so we want the gradient for the noise of medium scale to start at a certain distance and fully influence the scene somewhere between that point and the fog fade length distance. To do that, we need to subtract the start value from the main gradient and divide it for the length we want to give it. We can visualize the area covered by the gradient to see if we like it. The medium-tiled noise will be in influence on the surfaces placed nearer than these, and at full power from this point on. Now let's duplicate these nodes to make the last gradient we need. And let's use some other values to drive the most tiled noise. In this case, we want it to start influencing the scene as soon the previous one has reached the full power and cover all the remaining area. So the value of the start is the sum of the start plus the duration of the middle gradient, while the duration is the value remaining to reach 1. Let's preview once again our new gradient. Very good, looks like a reasonable spatial subdivision. Now, to apply these gradients to our new texture samples, we have to multiply them to their respective noises. And finally, we can combine these three textures. Let's go for our simple average of the noises. And take a look at what we have in the scene. The fog looks a bit dark now in the foreground. That's because there, with a simple averaging of the values, we are basically reducing the fog intensity by a third, since two of the noises are completely black. A better approach in this case will be to opt for a weighted average. In that way, we'd combine the noises giving them different importances depending on how far the current pixel is. To achieve that, first of all, let's assign to each texture an importance value, which for the time being will be 1 for all of them. Now, let's multiply the two scaled noises' importances by their respective gradients. That will make their importance go down where they shouldn't be applied. After that, we have to sum between them all the scaled importances. We can see the result of this operation as the total amount of importance present in every pixel. Parallelly, we have to multiply each importance by the respective noise. And sum all of them too. We can see this other value as the total amount of noise present in each pixel. Lastly, divide the total noise by the total importance to have our weighted average. Looks like the fog has returned to its proper intensity. Last thing to do, if we want, is to tune up a little bit the importances of the several layers. I'd say that they have less importance the further we look, since the furthest layer will be somehow occluded by the preceding ones. Let's now take a minute to admire our masterpiece. Look around, very cool. Move a little bit and... yes, apparently it's not over yet. As you can see, the fog looks perfect when rotating the camera, but as soon we translate it, it is immediate to notice that the fog mask is coming with us. It is not disturbing as before with this spherical mapping, of course, but still. This is a very interesting problem to solve because, see, we're trying to reproduce a volumetric effect, but without making it actually volumetric. And, in case you're wondering why we're looking for a workaround, well, for a volumetric effect of the scale of the entire world, I'm pretty sure we could say goodbye to the real-time feeling of the rendering. Now, I have to say that it required a lot of thinking and experimenting, but after a while I was able to find a solution to the problem that's satisfying to me. Let me know if you find that interesting too, and if you would have taken another approach. That said, let's proceed with the tutorial, but I have to warn you, the difficulty is going to spike quite dramatically from now on. The base idea of this solution is to unbind the sphere that generates our UVs from the camera and make it fixed in the world. And not only that, we're going to divide the world space in a giant 3D grid, with each cell containing its own sphere. Then, to mask our fog, we're going to display only the sphere of the cell that contains our camera at any given moment. How does that sound to you? Cool? In case you're wondering about how something like that is even possible, let me give you a hint. We're going to apply the magic of the recasting. Putting aside the dramatic talks, let's translate all I said to practical terms. To fix the sphere, our shader has to be able to calculate for each pixel which part of the inner surface of said sphere, located somewhere in the world, it's looking at. That, in even more practical terms, means finding the point where a straight line, starting from the camera and directed towards the pixel, intersects the sphere. That's right, you just found a real-life application for all that useless math they made you study in the high school. For all of you that really need to refresh that knowledge to fully understand this section of the video, I'm sorry, but going through the solving of that in detail will take hours. So, for this time, I'll just jump straight to the solution, but please, if you're interested in the topic of the math for video games, let me know in the comments and I'll do some specific tutorials on that. Going back to the system of equations, once solved, we get this formula. Let's translate everything to material nodes. T represents the distance from the camera at which we hit the sphere surface. So now we can transform it in a vector with the camera pixel direction and add it to the camera position to have, for each pixel, the world position of the sphere surface. If we now subtract from that the sphere position and normalize, we get the direction from the sphere center to the surface. And that can replace the camera vector for the calculation of the spherical coordinates we were doing before. Let's leave aside the multiple layers for the moment and let's hook the new coordinates up to a single texture sample. I believe it is a bit hard to understand what's going on just by looking at the fog, so let's hook these new coordinates directly to the emissive to visualize them. You can see finally the sphere is not coming with us, but we have the sensation of moving inside it. And if I move more than a certain threshold, we switch grid cell and suddenly we are in another sphere. Now, to re-implement the same fog layers as before, we just need to copy-paste this new bit of code 2 times and give each sample its own. If you're wondering why we're not using 3 times the same UVs, that's because in this way we can give each layer a different grid and sphere size, so they have a different parallax. Let's wander a bit around the scene and, as you can see, we still have some problems. The fog mask is really cool until we don't swap cell in the grid. At that moment we clearly see it snapping to a different sphere. How could we possibly solve that? We clearly need to find a way to smooth the transition between cells. If you have any ideas on that, once again, please write them in the comments below, since I'm really looking forward to see and discuss them. The solution I found, I have to say, required all my lateral thinking and it wasn't really easy to pull off, but here it is. For this, I was inspired by something that every GPU does to every texture by default, and almost for free. I'm talking about the bilinear interpolation of the pixels. If you're not familiar with this thing, here's a brief explanation. The bilinear interpolation is the algorithm the GPU uses to blend the pixels of a texture between them, so they don't look as distinct squares. We can turn it off to see its effect. When the pixel of the texture is bigger than the pixel of the screen, the GPU doesn't just display that, but looks also at its neighbors and based on their relative distance displays a color which is a blend of them. This is exactly what we're going to try now. Look at the adjacent sphere cells too, to display a combination of their masks. The only difference and added pain on implementing this feature is that we will have to do that three-dimensionally. So, by all means, we are going to write down a trilinear interpolation for our fog mask. First of all, given the high number of recastings we are about to do, let's move the nodes into a material function. Secondly, we have to make some edits to that, to account for a couple of things. Firstly, we need to make sure that the grid resolution is smaller than the actual sphere size, so they overlap each other. If they don't, recasting the neighbor sphere will be pointless, since the camera will be outside of them and so unable to see their inner surface. Secondly, we need to add the possibility to offset the camera position, to recast from a different cell than the one we are actually in. Cool. Now we can calculate all the sphere we want without losing our mental sanity with the amount of nodes that it would require. The sphere to recast are 8 in total, 2 to the power of the number of dimensions. The first one is easy, it's just our usual recast. The only difference is that now we're using the material function for that. To recast the other ones, we need to run some math first. To calculate the offsets, we need to apply. We need a gradient that gives us the normalized position of the camera relative to the current cell center. To calculate that, we have to divide the camera position by the cell size, so that the fractional part for each component goes from 0 to 1, from one side of the cell to another. Then we subtract from that the integer part, calculated by rounding the number, so the output goes from minus 0.5 to 0.5, from side to side of the cell. In this way, the sign of each component will tell us, for each axis, which neighbor cell we have to look at. For example, the Y component will be negative when our camera is on the left half of the cell, so our shader will know to look at the neighbor cell on the left of the current one. The very same thing applies for the other two dimensions. Now, to identify each cell, we have to create all the combinations of axes by multiplying these signs with some vectors that select the components that keep the values with a 1, and the ones that don't with a 0. After that, we just have to multiply each one of these results by the sphere size to obtain the offset for each neighbor cell. Each one of these go into an instance of our recast material function. And each one of these material functions will do as a UV input for one texture sample. Last thing we need to do is to figure out how to combine everything together. For that, we need to go back to the node we mentioned about putting the normalized camera position relative to the cell center. Before scrapping its actual value to just retain the sign, this node gives us a number that goes from -0.5 to 0.5 for each position component. That's a perfect place to start from. This time we need to scrap the sign though, while keeping the value, which can be doubled to push it in a 0-1 range. Now we have to create a concatenation of linear interpolations using these gradients. We can start with the first component, the x-axis, which will be used to lerp together in pairs our texture samples. Be careful to lerp together the masks that have cells coordinates differing by only the first component. The results of these 4 lerps have to be now furtherly lerped by the second component for the y-axis. One last lerp has to be added for the last dimension. Sadly, there's no way I could find to not make this look messy, but we can finally hook everything up and have a look in the scene. I don't know about you, but I think all this hard work is finally paying off. The fog finally looks as something that is in the scene, and we are able to walk through it. Just for completeness, let me visualize the spheres once again to make you understand better what's going on. It's a bit trippy, but you can hopefully understand how now the transition from one sphere to the next is being nicely smooth. I leave to you the re-implementation of the other 2 layers of the fog mask to properly finish this shader. It shouldn't be too much of a problem if you were able to follow me until here. Of course, we could push even further the look of this fog, both for variety and for prettiness. How will you add a random offset to the UVs of each sphere, for example? Or how would you fake its interaction with the light? Let's chat about that, and maybe these topics will be discussed in future videos.